Hi, welcome back to our channel Tech Sense Studio. Good day everyone. Our project is titled, like you guys know, food temperature and humidity monitoring system. The main objective of this project is measure and monitor temperature and humidity inside the shoe environment, also known as food microclimate, using a sensor based system. As shown in the setup, the system used an ESP32 microcontroller connected to a temperature and humidity sensor, assembled on a breadboard and powered through a USB connection. The sensor is designed to be placed near the food area to capture real-time environmental data. At the current stage, the hardware assembly has been successfully completed and all components are properly connected and functioning. In addition, the software and programming are already working and the system is able to read and display temperature and humidity data correctly. However, real food testing has not yet been conducted. At this moment, the project is still in the development and validation stage. The main focus is to ensure that the system is stable, accurate, and ready to actual experimental testing. At this stage, the system design implementation have been completed and the project is ready for experimental testing in the next phase.
Hello everyone, in this session I will explain the hardware integration and readiness of our food temperature and humidity monitoring system. First, I will introduce the main hardware components used in this project. The system is controlled by an ESP32 development board which acts as the central processing unit. The ESP32 is connected to a laptop using a USB cable. This connection supplies power to the board and allows serial communication for monitoring system output. Next, two sensors are mounted on the breadboard and connected to the ESP32. The first sensor is the DHT11 sensor, which is used to measure both temperature and humidity. This sensor is important for monitoring changes in heat and moisture within the food microclimate. For the DHT11 sensor wiring, the VCC pin is connected to the 3.3 volt pin on the ESP32, while the ground pin is connected to the ground. The data pin is connected to the GPIO pin 4 on the ESP32. An optional 10 kilo ohm pull-up resistor is placed between the VCC and data pin to help to stabilize the signal. Next, the second sensor used in this system is the DS18B20 temperature sensor, which provides more accurate temperature measurements. For this sensor, the VCC pin is connected to the 3.3 volts and ground pin is connected to the ground, and the data pin is connected to GPIO pin 5 on the ESP32. A 4.7 kilo ohm pull-up resistor is connected between the VCC and data pin, which is required for proper communication. All components are placed on the breadboard and connected using jumper wire. This setup ensures secure electrical connection and allows easy modification if required. When the system is powered on, LEDs indicator on the ESP32 lights up, confirming that the board is receiving power and operating normally. Initial checks also shows that the sensors respond to the environmental changes, indicating correct wiring and communication. It is important to note that no food testing is conducted at this stage. This demonstration focuses only on confirming that the hardware is complete, stable, and ready for the future testing. In conclusion, the ESP32 sensors, pull-up resistors and power supply have been successfully integrated. The system operates without errors and is fully prepared for the next phase. Thank you.
Assalamualaikum and hello everyone. My name is Fahmi. In this video, I will demonstrate the functional testing of the sensor used in our food microclimate system. This test is conducted without using a human food. Okay, the objective of this testing is to verify that the sensors are functioning correctly and produce reasonable temperature and humidity values and respond to change in the surrounding environment. Okay, for the system consists of an ESP32 microcontroller, a DHT22 sensor for temperature and humidity measurement, and a DS18B20 sensor for temperature sensing. The sensor output are observed through the Arduino serial monitor. Okay, at the beginning, before we touch the sensor are tested under ambient room condition as shown in the serial monitor. The temperature and humidity reading are stable and within a reasonable range. Okay, for next step, I will touch the temperature sensor with my hand to introduce heat. So we can observe that the temperature value increases gradually, which confirm the sensor response to temperature change. After we touch the sensor with my hand, after removing the hand and exposing the sensor back to air, the temperature reading decrease and return towards the ambient value. Okay, in conclusion, preliminary testing under ambient condition confirm that the sensor respond correctly to temperature and humidity change. The value observed are reasonable and stable. This validate the functional performance of the sensor. Okay, that's all for me. Thank you.
Hello, good day everyone. My name is Firdaus bin Jamarudi. I am from class IC5B, and for my part, I will explain the software logic and data processing of this system. The software for this project is developed using Arduino IDE and run on an ESP32 microcontroller. The main function of this software is to read data from temperature and humidity sensor, process the data correctly and prepare it for monitoring and future cloud-based application. As shown here, the libraries used allow the ESP32 to communicate with the sensor, manage Wi-Fi connectivity, and support data transmission to the Blink platform. Next, the sensor configuration is defined in the code. The DHT11 sensor is used to measure temperature and humidity, while the DS18B20 sensor is used to measure temperature with higher accuracy. This configuration ensures that the ESP32 read data from the correct hardware connection. I will now show the main function responsible for sensor data acquisition. In this function, the ESP32 reads temperature and humidity data from both sensor and at a fixed interval of 1 second. The readings are processed and checked by ensure that the value are valid before being used. After processing, the sensor data is displayed on the serial monitor. This step is important for system validation as it allows us to verify that the sensor responds correctly to environmental changes and the reading and reasonable and stable. The readings are reasonable and stable. The system is also programmed to connect to a Wi-Fi network automatically. Once connected, the processed sensor data is prepared and sent to the Blink platform. This shows that the software is ready for future real-time monitoring and cloud data. Even through cloud analysis is not the focus at this stage. Finally, the main loop ensures that the sensor reading, data processing, and communication processes run continuously. Overall, the software has been successfully implemented and tested. At this stage, the focus of the project is on software validation and system readiness rather than conducting actual food experiment. Thank you.
Hi everyone, my name is Fuad bin Norazalan. For this part, I will explain monitoring and visualization system using LabVIEW. Firstly, this is a LabVIEW front panel which function as the main user interface. On this panel, we display simulated temperature and humidity value using numeric indicators and waveform chart. This indicator allow user to view the current sensor reading clearly, while the graph show how the data change over time. Okay, next, this is a block diagram. In the block diagram, we generate simulate temperature and humidity signal to represent real sensor data. These signals are then processed and continuously updated on the front panel. This shows how LabVIEW handles data flow from input to visualization. LabVIEW is used in this project because it provides a powerful and user-friendly environment for visualization. By observing the graph, user can easily monitor data trends, detect fluctuation, and identify abnormal patterns which are important for analysis and decision making. Although the data shown in this system is simulated, the overall design is ready for real implementation. In future work, the simulated input can be replaced with actual sensors such as temperature and humidity sensor without major change to the system structure. In conclusion, this LabVIEW interface demonstrates an effective way to visualize, monitor, and analyze sensor data, and it can be further developed for real-time monitoring application.
Today, I will be explaining about updated sensor placement, why to and hill only, what type of data each position give, why this design is better and simpler, 5. Safety and readiness for real experiment. For this part of our project, I will explain the updated sensor placement design. In our final design, the sensors are placed at two main locations on the fruit, which are the two area and the hill area. The design was chosen to simplify the system while still ensuring meaningful and reliable data collection. The two area is selected because it is one of the most sensitive parts of the fruit. This area has a higher concentration of sweat glands and is more exposed to temperature changes. While the hill area is chosen because it is a major pressure point of the fruit. During standing and walking, the hill area supports a large portion of body weight, which cause heat to accumulate over time. This makes the hill suitable for stable temperature measurement. In addition, the hill provides a relative flat and firm surface, allow better sensor contact and more consistent reading. In this updated design, the art area is excluded. This decision was made because the art has less direct contact with surface and lower sweat accumulation, which may lead to inconsistent or less reliable measurement. By removing this location, the system becomes simpler, easier to integrate, and more focused on the most critical measurement. At the current stage, the sensor placement is conceptual and focused on design validation. For now, actual human fruit testing has not yet been conducted. This is to ensure that all sensors are properly calibrated and that electrical safety is fully verified before performing real experiment on a human fruit. Overall, this updated sensor placement design balances measurement accuracy, a system simplicity, and a user comfort, and it prepares the system for future real-time food monitoring experiment.